For problem 5.44, we have the threshold voltage for the transistors in the circuit. We have the process transconductance for that particular transistor in the circuit. The transistor has a length of 0.4 micrometers and a width, so the channel is 0.4 micrometers in length and 5 micrometers wide, so length and width here. And the circuit that we have is this one here. So here we have the gate, here we have the drain, and here we have the source. So the gate here is grounded. Here at the drain we have a drain resistor and a voltage supply that is +1 volts, and down here we have the source resistor with a voltage here that's -1 volt. And in this particular problem we need to find RD and RS so that the current flowing through the drain and the source are 0.1 milliamps, and VD, voltage at the drain terminal, is 0.3 volts. So this last assumption, this last non-condition here, basically tells us that this voltage here, VD, is equals to 0.3 volts. So if we want to obtain the current flowing through the drain, this current here, ID, we can apply Ohm's law and isolate RD, because remember that the voltage across this RD, so let's call VRD, is equals to 1 volt, right? The potential at this terminal minus the potential at this terminal, which is VD, so it's minus 0.3 volts, right? This is the voltage, and that voltage is equals to the drain current times the drain resistance. And one thing is that I didn't mention at the beginning of the problem is that we can assume that the transistor, the MOSFET, is operating in the saturation region. So we are going to assume that VDS, so let me write up here, so just a second. Let me change this one here, down here. So let's assume VDS greater than the overdrive voltage, and that the channel modulation, for simplification, is 0. Okay, so this one here means saturation region operation. In this parameter here, it's just that the current at the drain, first in the saturation region, we won't have that factor that changes the output resistance, right? That's that the current ID keeps increasing if we keep increasing VDS. So we are ignoring that effect. So going back to the analysis of the circuit, so we are calculating ID here, right? ID times RD gives us the potential difference across this resistor at the drain. And we know the voltage, 1 volt here, and this voltage here is a parameter from the problem. So we want to have this VD here 0.3 volts. So we are going to design RD and RS to give us that. And from this equation here, we know that RD should be equals to 0.7 divided by the current. That's also a parameter from the problem, right? Up here. So this gives us a resistance that is 7k ohm. So that's the first term that we need to find out here in this problem. Now for RS, we need to remember that the overdrive voltage is equals to VGS minus the threshold voltage, which is the same as VG minus VS minus the threshold voltage. Now if we look at the circuit, the gate here is grounded, so this one here is actually 0, okay? And the overdrive voltage is equals to minus Vs plus the threshold voltage, okay? Now, how do we calculate the overdrive voltage? So remember that at the saturation region, ID is equals to 1/2 the process transconductance times the aspect ratio times the overdrive voltage squared. We know ID, we know the process transconductance, we can define the aspect ratio because we know W and L. We can define the overdrive voltage. So the overdrive voltage is equals to square root of 2 times ID times L, the length of the channel, divided by the process transconductance times the width of the channel. If we substitute the parameters that we know, this becomes 2 times 0.1 milliamps times 0.4 micrometers, that's the length of the channel, divided by 400, the process transconductance, so it's microamps per square volts, times 5 micrometers, that's the width of the channel. So if we calculate V overdrive, we get a V overdrive of 0.2 volts. Now because we know the V overdrive and we know up here, right, this equation here, so let me write it down here. So V overdrive is equals to minus Vs minus the threshold voltage. We can calculate the source voltage, the voltage at this point here. So Vs is equals to minus V overdrive minus Vt, the threshold voltage. And in this case, Vs is equals to minus 0.2 minus 0.5, which is minus 0.7 volts, right? So now that we know this potential here, Vs, and the current that flows in the drain is the same current that's flowing in the source, ID equals 0.1 milliamps, we can calculate the value of RD that, based on this potential difference here, gives us the same value of ID flowing here on at the source. So RS times ID should be equal, so this is a voltage, right, Ohm's law, should be equals to Vs minus those minus 1 volts. And Rs in this case is Vs minus plus 1 volt divided by ID, which is 0.1 milliamps. And because this one here is minus 0.7 volts, Rs is equals to 0.3, 1 minus 0.7, 0.3 divided volts divided by 0.1 milliamps, and this gives us 3 kilo ohms. Now remember that we assume saturation region operation for the MOSFET. So let's see if VD minus Vs is greater than V overdrive. Now VD, we know it's the parameter that we want, is 0.3. Vs is minus 0.7. That should be greater than the overdrive voltage, which in our case is 0.2 volts. And we see that this is true, right? So 0.3, this one here becomes plus, so 1 volt is greater than 0.2 volts. And this condition here is satisfied. Okay? So that's the solution for problem 5.44.